I hope you can see my screen. I hope you can hear me. Hello?
Yeah. Yes,
Okay,
we are.
fine. All right. So I'm just trying my pen. Sometimes this gives me a little problem. I'm trying my pen. So if you can see on your screen, let me know. Okay. Guys, can you see my pen?
Yes.
Okay. Okay. Sorry for that. Sometimes it's just misbehave like that. Okay. So let's get started. As I said, we're going to deal with clustering today. Let me go back here. Okay, so we're going to deal with clustering, and we will talk about the K-means clustering, and then we also talk about the hierarchical clustering. So let's before we go to the code, before we get hands-on, let's get the intuition behind this before we get to the code. All right. So we are going to the OneNote, and then we will see a little intuition behind this clustering. Okay. Okay, so when we talk about clustering, just think of clustering as sets, right? Where we have same or similar items that we group together, right? So we cluster items together. So let's say we have say item A, or we have say set A, right? Which consists of some items, here, right? Then we have say B, which also consists of some items here, all right? Consists of some items here. So some items which are similar to each other will be grouped here, all right? So maybe some items which are similar to each other will be grouped together here, right? Based on some characteristics that we define, right? And then some items which are also similar together will be defined in B, right? So let's take for instance maybe B represents, let's say B represents say pregnant women, all right? All right, so maybe you have say a website, right? You have a website, and then you sell some stuff, just like Amazon website, where you can go there and then buy some stuff. So let's say we have pregnant women who will come there and then buy stuff. When pregnant women come to your website, they have some items that they buy, right? So some pregnant women, let's take India for instance, right? So we will be having a lot of pregnant women that will come to your website to buy stuff. So maybe they will buy some baby clothes, all right, maybe some baby clothes, some baby oil, something like that. So they'll have some similar items that they will buy, all right? So if you have this buying behavior, right? If you have this buying behavior that you have put here, right? You can actually group those people who buy these items, right? You can group them as having one buying behavior, right? You can cluster them, all right? And then let's say we have another group, like another group that comes to your website and buy say phones, right? They come there, they buy phones, they buy phone charger, they buy say they buy laptop, right? Something like that. So these are also having different buying behavior. You can also group them together, all right? So this become cluster, this become another cluster, right? Based on their buying behavior, based on what they do, right? So think of clusters as objects that are having similar characteristics that we can group them together, all right? So that's all about clustering, and we have several ways of grouping these together when it comes to machine learning algorithm, right? And this is actually based on the distance that one item is having according to, with respect to the other item. If you remember when we were doing the KNN, we talked about some, my pen is misbehaving again. Okay, get this one off.
Euclidean distance.
Yeah, my pen has actually frozen. It sometimes misbehave like that. I think I have to uninstall this pen and then do it again. I just want to get rid of this one. Let me just create another one here. Okay, so this one, let me actually get everything off. Okay, so let me try this one and see. I hope it will work fine. And then let me clean it. Okay, I think this one is working. Okay, so as we did, we were talking about in KNN, we have several distances. So if for instance we have, let's start with say two-dimensional space, right? Let's start with two-dimensional space. So let's say we have these points, right? We have these items that are having some characteristics, right? They all have some characteristics, right? Okay, so now if we want to, group them together, let's say we have other items too, like say blue or something like that. Something like that. Okay, so we say that okay, by common sense we can say that all the blue points they look alike, so we can put them into one cluster, and all the black points also look alike, so we can put them in one cluster, right? But we want the machine to learn from it, so that if say we have a new point, say red, right? A new point red here, how can the machine actually cluster this into a blue cluster or cluster it into a black cluster? All right, so it will do this based on the distance, right? It will just measure the distance that is having, the distance from this red to the next one, to the next one, to the next one, like that, right? It will measure the distances like that. And then it depends on how many centroids. We will talk about centroids later on. So it depends on how many centroids that we are actually considering, or the distance that we are actually distance measure or criteria that we are using, right? Then it will assign this red point to either blue or black. All right, and as we said in the KNN class, right, we have several distance measures that we use in this case, right? We have several distance measures that we use. One is Euclidean, right? And I'm sure you are familiar with this, right? One is Euclidean. One is Manhattan. We also have what is called the Chebyshev. Let me write this thing a bit clearer for you. Okay. And then we also have the cosine similarity, all right? We also have the cosine similarity. So as we discussed, it's just the same intuition, right? So let's say we have a point here. We have a point here, right? We can call it A. We have another point here. We can call it B, all right? And then this A, obviously, we have, this is X, this is Y. So this is actually going to consist of X and Y. All right, it's going to consist of X and Y. So let's say X1, Y1. This is also going to consist of X and then Y, right? X and Y. So let's call this S2, Y2. All right, so if we want to measure the distance from A all the way to B, then obviously it's from, if we are considering Euclidean, then it's going to be X1 minus X2, all right? You find the square of it. The square will actually nullify it if you use X2 minus X1 or X1 minus X2, since you are finding the square of that, right? Plus, and then we also have Y1 minus Y2, right? Y1 minus Y2, find the square of that, and then you find the root of that. So this becomes, I mean, the Euclidean distance, right? So Euclidean distance will define this, right? We'll define the distance as that. But if it is Manhattan, right? If it is Manhattan, then Manhattan will say, instead of going straight from this part to this part, then Manhattan will go this way, then it will go up like that. All right, so it will find X1 plus S2. I mean, S1 minus, let me clear this, minus S2. It will find absolute value of that, right? Then it will also find Y1 minus Y2, then it will find the absolute value of that. So if there are several points, let's say C is also there, then it will continue like that, right? So it will continue like that. If they are added, it will continue again like that, continue adding them like that. So that's what Manhattan distance will also do, all right? And then the this one, the Chebyshev, is just the summation of that, right? So that one is actually going to give you this, the summation of X1 minus S2, right? Plus Y1 minus Y2, okay? So if it is a lot, then you can simplify this as that. I'll say X1, or let's use Sn, right? Or Si minus say Xj, right? Something like that. Then P, because we don't actually know. If it is just like this, it's obviously exponent 1, right? So we don't know the exponents that we're going to use, so we represent that with P, right? So if this one, if the P here, right? If the P here is say 2, right? For instance, if the P here, let me clear the P. So if this P is say 2, if I say 2 here, then obviously this one is the same as this one, right? It's just the same thing. It's just the same thing. So this one will become as Euclidean. If this is 2, then it becomes as Euclidean.
It's
but
9 o'clock.
If it is 1, right? If it is 1, then obviously Xisj, right? The summation of that is just the same thing as the Manhattan distance, right? It's just the same thing as this one. Okay. And then the cosine similarity, of course, is just using the angle, right? So let's say we have point A here. If we have point A here, and then we have point B here, then we find the angle which is between these 2 points, right? We find the angle between these points, right? So that's going to be the cosine of that angle, right? And then if I mean, it depends on the size of this angle, right? So the smaller the angle, the similar these 2 points are, right? So that's what the cosine similarity will actually do. Okay. So with that, I mean, that's basically what this algorithm will do to find or associate a new point with the existing point, right? You just calculate the distance. Okay. And there are types of clustering, right? There are types of clustering, but so far the major or the main clustering algorithms that is popular, right? Basically 2, which is the K-means and the hierarchical clustering, right? So we will start with the K-means, right? We start with the K-means clustering. So before we do that, let me go back to one note here. Use black. So talking of types of clustering. All right, talking of the types of clustering. Sometimes you hear something like this. Let me do it this way so that it's very similar for you. You hear something like this. You hear something like connectivity based. Connectivity based clustering. Right, and this example of this connectivity based clustering is what we refer to as the hierarchical, right? Just what I just mentioned, right? Hierarchical clustering. Right, and then you also hear centroid based clustering. All right, and example of this one is the K-means clustering. Okay, example of this is the K-means clustering. So basically these two are the ones that you basically hear on in the industry. Basically these two are the ones that you hear, either hierarchical or K-means. All right. So let's before we go to K-means and then we get into details with the hierarchical clustering. We will do hierarchical clustering from next week, but let's first have an overview of that before we do K-means into detail today. All right. So let's see what this connectivity base is all about. All right. So as we discussed earlier on, right? Let me bring this one here. Okay, this thing is doing it again. Guys, just give me 1 minute. This thing is freezing again. I have to uninstall this. Okay, I think it's better now. Okay, so as we're discussing above here, right? As we're discussing above here, let's draw a new one. Let's draw a new line here, right? Okay. So what connectivity based will actually do is that if we have points like this, right? If we have points like this, and then we have some points here. So what connectivity base will do is that it will try to connect, right? Connect each point with the other based on the distance. So it will see, let's pick this one, this black, right? It will say that, okay, this black point is closer to this point, so they are similar to each other. This one is closer to this, they are similar to each other. This one is closer to this, they are similar to each other. This one is closer to this, they are similar to each other. But it will not connect this one to, say, this point, right? Because they are further apart. Unless we actually want to move from the small group to the larger group, right? Otherwise, it will just group the similar ones, the smaller distances, before it will gradually increase it, right? Before it will gradually increase it to connect to the larger group, say from say this point all the way to this point, connecting them. All right, so that's what connectivity will actually do. So let's just pick a simple example to get to understand that. Let's say we have this box here. Okay, now let's say we have a point here. let's say we have a point here, let me name it A. And then let's say we have another point here, let me name it B. All right, and then let's say we have another point here, let me name it C. And then we have, say, another point here. All right, another one too here. Let me call this one D. All right, let me call this E, let me call this F. All right, so let's say we have these points. All right, so what connectivity base will do is find the ones that are closer to each other, right? Try to first connect them. So let's say, as we can see with just our eyes, right? Just eyeballing this, we can see that A and then B, you can see E and F, they are closer to each other, right? So what connectivity base will do is to actually connect these two, right? Connect the ones that are closer to each other first. All right. Then after that, it will see that, okay, if you consider this, if you consider E, F, and then D, they are closer to each other, right? So it will connect E, F, and then D. All right. Then it will say that, oh, it can, this E, F, D is also closer to this, it's also closer to C, right? It's also closer to C. So maybe it will now connect with this, right? Now you see that the whole of this can now be connected to this if we want to connect all of them to as one, right? If we're going to connect all of them as one. So that's what connectivity will actually do. Okay, and we can actually do this in build it from down to up actually, or from up to down actually. So let's say this A and B, right? We can put, say, this point A and B. Let me go a little bit down. Okay, so let's say we have points here. We have this point A here, right? I'm just drawing the same thing here, the same A and B, right? So A and B are closer to each other here, right? So I'll put B here. Then let me put, say, C here, somewhere here, all right? Then E and F, right? E and F are closer to each other, so so let's bring D first. Let's bring this first. So A, B, C, D, right? So let's do that. It's a bit further apart from C, right? And then we can find E and then F, right? Being closer to each other here. Okay, being closer to each other here. So what it will do is to connect the ones that are first closer to each other, right? To connect these two. Then after that, since E and F are closer to D than C, right? It will connect this with that. Okay. Then after that, it will connect, since now D, E, and F are now closer, it will now connect with this. All right. It will now connect with that. Now we can connect these together, right? We can now connect these together. Okay, we can now connect these together. And this is what we refer to as the dendrogram. So this is what K-means will do, right? This is what K-means will do. So this is more like a hierarchy, right? It's more like a hierarchy. So we call this one the hierarchical clustering. All right, we call it a hierarchical clustering. Let me off this thing. All right. I hope up to this part is clear. Is there any question anyone wants to ask?
No, it's clear.
Okay, all right. So that is dendrogram, and we refer to this one as hierarchical clustering. All right. So having talked about that, now we can move on to what is called the K-means. All right. We can move on to what is called the K-means. Okay, so with K-means, as we mentioned here, right? With K-means, it deals with the centroid, right? It deals with what is called the centroid. Instead of connecting, it deals with what is called the centroid. So let's try and then understand what that means. Okay. So instead of connecting each of these items based on the distance that is existing between them, right? Based on the distance between A and B, and then say E and F, and then say C and D, something like that. It actually base this algorithm on the centroid, right? So let me draw some points so that we get to understand that better. My pen is doing this again. Okay. So let's say we have some scattered points in here. I'm using two-dimensional space most of the time because it's easier to visualize, and if you want to use um, say three-dimensional space or 4 or 5, it's actually difficult. So that's why I keep on using the two-dimensional space, right? So what KMeans will do is to actually put centroid or central point in here, right? So let me use this, right? Central point. So let's say we put one point here, one central point here, right? Then say we put another central point here. Then we put another central point here. All right, so for hierarchical clustering, we say that we consider the distance, right, between these items, right? So each of these points, we find the distance between them using the Euclidean or any of the other distance measures. But with this, we find the distance between each of these, right? Between each of these and the centroid, right? Between each of these points and then the centroid, right? We find the distance between each of these points and then the centroid. So here the centroid is the most important thing for us, right? So items that are closer to this centroid will be grouped together as similar items, right? Items that are closer to this centroid will be grouped together as similar items. And this is going to be run iteratively several times based on what you specify, right? So items that are closer to this centroid will be grouped together as similar items. So if we want to see similar items in this cluster, then we will see which centroid it's associated to, and then we will consider which items are also associated to the same centroid, and then we can see that, okay, this item is closer to this item and is similar to this item. All right, so this is what KMeans will actually do, right? This is what KMeans will actually do. It will put centroid, that is central point, right? To put centroid there, and then it will associate each of the points to one of the centroid based on the distance of each of the points to the centroid. All right. I hope this part is clear, or is there any question? Okay, so what we try to do is to actually minimize this, right? Remember, each of the algorithm is having a way that we try to minimize the error, right? So what we try to minimize over here is the distance between each of these points and the centroid, right? The distance between each of these points and then the centroid, right? It's nothing but the variance, right? So this distance between each of the points minus the mean, right? If you find the sum of that, right, and you divide it by the total number of points that are there, right? This is what we try to minimize, right? We try to minimize this. All right, so for each of the algorithm we have a way that we minimize the error that is existing in each of them. Okay, so let me show you something here, and then let me show you something in the Jupyter notebook. Okay, so I have this simple code here that I'm going to run. Then I'll show you what it's doing here. Okay, so if I run this code, right, this the window that I will get, right, out of the code that is there, right? So this is one of the, let me minimize this. I don't want to see this thing here. Okay, this is just a Python GUI that's this simple code can actually help you to get. Let me bring it here. Okay. So with this code, I just generated some random numbers here, right? I just generated some random numbers from 1 to 200, right? Some 100 random numbers, right? I generated 2 of them. So I create a dictionary here, right? So 1 in A and then 1 in B. They are all random numbers between 1 and then 200, right? 100 of them, all right? So, and then I'm using this package, right? Package called Kenta, right? That's what I'm using, right? Then I use this file dialog to create that, right? So if I run this simple code that I have here, right, then I will be getting this window here, right? So I just want to show you how this centroid is actually going to being associated, right, with this 100 and 100 random numbers that I just generated, right? So if I say that I want, say 5 or maybe six centroid, right, or 6 clusters, right, and then I run this. Right, now you can see over here, we push this one down. Now you can see on your screen down here, right? Okay, now you can see that we have 5 centroid. Look at the red points that we have here, right? We have 1, 2, 3, and then 4, 5, right? That's 6 actually, right? We have 6 clusters that we have, right, with different colors being associated. However, if I say that I want say 5 clusters, right? If I run 5 clusters, now you can see that the second one that just came is now having this. It's now having 5 clusters, right? We have one here, we have another one here, right? Then we have another one here, we have another one here, and then another one here. Okay, so we have different clusters that we've been able to get. If I say that I want say, let's go to say 3 clusters, right? Now you can see that we have 3 different clusters that we've been able to associate this point with, right? So we have one here, we have another one here, and each of these clusters are having data points, right, associated to it according to how close these points are, right? So if you see, let's say this one, all the points that are closer to this centroid have been associated with it, and you can actually see that some of the points probably, if you take this point, for instance, this point here, for instance, right, maybe it should have been associated with this. If you run it iteratively, right, it can go that way. Or maybe let's take this point. Let's take this point here, right? This yellow point here, right? Maybe it's closer to this one than being closer to this yellow, this red point here, right? However, it's been associated with yellow, right? But it's not going to be this final. It's actually going to run this iteratively until the point that we cannot associate any data point to any other cluster again, right? Until it gets to some point that if you run the code, nothing will happen, all right? So in this case, if I say that I want, say, 2 clusters, right? If I want 2 clusters, now we can see that we have only 2, right? We have only the yellow and then the blue, right? Clusters, only 2 of them that we have here. Okay, so depend on the number of clusters that you want, your data is actually going to be grouped into different clusters, right? And choosing this number of clusters is very critical. Right? You need to know the number of clusters that is suitable for your data, and then you choose that that number of clusters for your data. All right, and there's a way to choose that. When we go to the code, I'll show you that. There's a way to actually choose that. So I'll show you that one. All right, so associating this point into different clusters is I mean is more critical, and there's a way to do that. Right, there's a different way to do that, and we're going to see it very soon. All right. Now let me show you this simple video here. Let me show you this simple video. I hope you can see my screen, right? Guys, can you see my screen? Can you see a new window on the screen?
Only we could able to see a K-means clustering window.
Okay, that's what I wanted you to actually see. So I mean, it's a video, so I'm going to play it so that you can see how these centroids will be allocated, right? So the intuition behind this is that you'll be having your data points scattered like this, all right? And to associate the centroids, right, is actually going to run behind, which you cannot actually see. But how this thing is actually being done is what is going to be demonstrated here. All right, and there's something that let me point out to you at first before I play the video. Right, you might hear this this theorem. Is the actually Leo's theorem. All right, you might hear this theorem on the field. Leo's theorem, right? What it's saying is that if you have your points, right, if you have your points scattered like this, right, and you want to associate these red points are going to be run iteratively until these data points are no more moving to like this point that you have over here, right? Let's take this blue point that you have here, right? If you say that you're going to run this code, say 15 times, right? If you run it the first time, this blue point might get associated with this centroid. If you run it again, it might get associated with this point. If you run it again, it might go back here. If you run it again, it might come back here, right? So if you do that several times, right, it will get to a point that when you run it, if it gets associated with this and you run it again, it's not going to come back. If you run it again, it's not going to come back. It's still going to be associated with this. And the same thing will happen to all the other points, right? So that's what Leo theorem is actually doing. And that's what the video is actually going to demonstrate. So I'm going to play that so that you get to know the intuition behind this, all right? So let me. So you can see that we have several points that is being displayed on the screen. All right, we have several points that is being displayed on the screen. So if you run it at first, it will just associate them with each of the points. Then it will try to combine some of the centroids, right? So that with the many centroids that you'll be having will be combined as one, all right? So you can see iteratively here, right? You can see that this thing, there's a running here, iteration is running here. And the number of Ks, you can see it's over here. You can see the number of Ks over here, right? And then how many data points that we have, you can see it over here. So the points will keep on shifting. It will keep on shifting until it will get to a point that it's not shifting anymore, right? And these things are going to happen at the background that you will not actually see with your eyes, right? Okay, so how you choose this K is actually critical, and I'll show you how this is done in the code. But before we do that, I'm going to show you something on the notebook, how that is being done, so that when we run the code, it will not be difficult for you to actually understand. All right. I have this simple one here too that you can actually see. Okay, this one also demonstrates the same thing, the same idea that we're just talking about. All right, this one that you can see on your screen. You can see over here that we have K to be 4, right? And then our data point is say 300, right? So if we are going to run this one, then see how it's also going to demonstrate the same concept, right? Okay, now you can see that there are some centroid, right? There are some you can see the centroid moving, right? That's what it's actually going to do. So you can see the iteration here, right? You can see, and then you can see the centroid moving like that, right? Different centroid being moved like that. Now you can see that although we are still iterating, but the centroids are not moving anymore. Okay, so I hope this actually um, gives you an idea of how things actually work at the background. Okay, so let's say we have our data points like this. Let me actually hide this. Let's say we have our data points like this. Now, if we have, say, one centroid, right? If we have one centroid, let's say this is a centroid. Let's say we have our centroid point here, our central point here. Now, if remember we said that we try to minimize the variance, right? That is the distance between each point and then the mean or the central point that we'll be having over here. All right. So if we have this point here and then we try to connect each of them, right? Let's say this is just one centroid. It means that the whole of this, right? The whole of this belongs to one cluster. The whole of this belongs to one cluster, and there's no. I mean, the variance here is going to be quite huge, right? It's going to be quite huge. If we have another point scattered here, right? If we have another one here, let me draw two of them so that you'll get to understand it well. So we have these points scattered here. Okay, so in this case, let's say we have the first one. Let me zoom out a bit here. For the first one, we have one central point, right? One centroid there. Now, for the second one, let's say we have two centroids, right? Let's say we have this one here, and then we have this one. All right. Now, instead of this distance, right, from maybe this point all the way to this, right, that's quite huge, right? And that in this case, if we do this, if we measure a point like this, you can see that the points are going to have small distances, right, as compared to this one that most of them will be having huge distances or huge variance here, right? The variance here is going to reduce, right? In the same way, if we have another point, right? If we have another one, if we have another scattered point here, if we have this, and then we try to have, say, 3 centroid, right? Say one is here, say another one is here, and then let's put one here. All right, if we have 3, then it means that it's actually going to be less, right? Very, very less. The variance is actually going to be very less as compared to the first one, right? As compared to the first one. So the more the centroids become many, the more, the lesser you get the variance. All right, so let's try and then put this one in a 2-dimensional space and then see. So let's say we have the centroids here, right? Let's say we have, say, one centroid, 2 centroid, 3 centroids, 4, say 5, right, and so on. Maybe all the way to say n, right, something like that. And then this part is actually going to be the variance, right? So the variance will be here. So whatever will be here will be the variance. Okay. So now if we have just one cluster, right? This represents the centroid or the clusters, right? So if we have only one cluster, it means that we have that's going to give us the largest, or the highest variance. All right. Now, if we have 2 clusters, it means that this variance is going to reduce. So maybe it is going to go somewhere here. All right. If we have 3 clusters, it means that it's going to reduce further. Right. If we have 4 clusters, it's going to actually reduce further. If we have 5 clusters, it's going to reduce further, right, until it gets to a point that is not making any significant reduction. All right. So we can actually connect this.
Actually, I have one question.
Okay.
How the algorithm decides the distance between the centroids?
The distance between the centroids.
Yes.
Okay, that one it depends on the number of centroids that you specify. So if you say that we want 5, actually the data points are not going to be like this, right? It's going to be in the data frame, right? It's going to have something like this, right? We have the column, and then we have the rows here, right? We have the rows here. And then we'll be having some data points inside, maybe some 700, maybe some 20, something like that, maybe 0.4. We'll be having several points in the row and then the column, right? So what the algorithm is actually going to do is to find the distance between these points, right? We have another one here. Let's say we have 10, we have, say, 100 here. We have some data points here, something like that. So what it's going to do is to find the distance between 720, 710, 700 and 100, something like that, 0.4, and then 111, 0.4, and whatever is here. It's going to do like that, right? So it's not actually going to calculate the distance between this, right? And depending on the number of centroid that you use. So if you say that you want 4, right? 4 centroid, then it's actually going to divide this data set into 4 equal parts, right? Based on the Euclidean, either of the distances that you specify. These are hyperparameters that you can actually change, right? Either you want it to use Euclidean to calculate this distance, or you want it to use the Manhattan distance to do this, right? It's actually going to do that at the background for you. So depending on the number of centroids that you decide, right, it will actually put these centroids. So the distance between this is not actually being calculated, going to be calculated. It's going to use what I told you earlier on here, the Elliott theorem, right? So it's going to be shifting this. So let's say the point initially was here, right? By running this iteratively, this point might move to somewhere here, right? And this one might move to somewhere here, right? So that the data that is around here will be in one cluster. The data around here might be in one cluster, something like that. All right, so the distance is not actually going to be fixed based on the position here, because the position itself is not going to be fixed. It's going to be moving, right? It can be moving down or moving up, something like that. And then the data points will be moving from associating from different centroids to different centroids. All right, so it's not actually going to be fixed. So when you are running the algorithm, you are going to specify the number of clusters that you want, right? So you will see something like n clusters, right? So the number of clusters that you want, you specify that, and also the number of iterations. So maximum iteration. So you see something like max iter, right? Maximum iteration that you give, right? So that's actually going to run, and then iteratively is going to be shifting these points, the centroid as well as the individual points, right? So it's not actually having a fixed position like one centroid is here, then one centroid is here, then we find the distance. No, it's not going to do that. It's going to be randomly shifting these points, right? It's either going to move up or going to move down, and then associating points to it like that. All right, and it's going to be based on what is called the Elliott theorem here. That's the video that we just saw. All right.
Okay.
Yeah, and if it's actually going to, the distance that is going to happen here is between this small point and then the centroids, right? So that's where the distance calculation comes from. All right. That's where the distance calculation comes from. And that's where either the Euclidean or the Manhattan or whatever distance you specify is going to be used, right? These ones are going to move randomly in the data points, right? It's going to be shifted. These centroids are actually going to be shifted. All right. Okay, so moving on here. So as I said, depending on the number of centroids that you specify, right? So if it is one, you're going to have high variance here, right? You're going to have high variance. So as the number of centroids keep on increasing, then the variance keep on decreasing, right? So just like you see here, if it is one cluster or one centroid, then you're going to have high. If it is two, it keep on decreasing. So you can see over here that is just decreasing like that, right? It's just decreasing like that. Okay, now it will get to some point that the decreasing, the rate of decreasing is not actually making any significant impact. There's actually not going to be a significant decrease here. So at that point where there's a sharp turn and then there's no significant decrease in the variance, it's that point that you need to choose. So in this case, maybe we can consider say 4, right? Then after 4, we can see that the rest are not actually significantly decreasing, right? If you see how steep this one is and how this one is a bit flat, right? So we can see that, okay, now the number of clusters that we want to use here is 4, right? Now we can choose 4 as the number of clusters, which will actually make sense, all right? If we say go beyond that, it's not actually going to make any difference. It's just going to give us huge clusters which does not actually make sense, right? For instance, as I said, there could be, say, pregnant women coming to your website who are buying similar items, right? But if you choose huge clusters, it's going to be like maybe some pregnant women, instead of buying baby clothes and then buying, say, baby powder and stuff like that, some pregnant women might end up buying phone. All right, so you might wrongly put them in different cluster, right? If you have a huge cluster, right, it means that if your data point is like this, right, if your data points are like this, and you say that, okay, I'm in this data point, I'm going to use, or I'm going to choose, say, I'm going to, let me use green here. Let's say I'm going to choose, say, 4 clusters, right? So you put one here, you put another one here, you put another one here, then you put another one here. Now, if these points are being associated with these clusters, right? If points are being associated with these clusters, you might end up having small groups, which does not actually make sense. Maybe the points that are being clustered into different groups, like the points here, which are being clustered into this group, are the same points or similar to these ones, which could have been put together. But because you specify huge clusters, right, they've been divided into that many clusters for you, which is actually not going to make sense. So you might end up having so many clusters which are not making sense. So we want to actually find the ideal cluster or the best cluster, number of clusters to use, right? So we use this kind of method, and this kind of method is what we refer to as the elbow method, right? So if you hear about the elbow method, it's just this one, right? So where there's a sharp turn, just like your elbow, right? Where you have your arm like that, and then I'm going down where your fingernails start to come, right? So where your elbow is, right? Where there's a sharp turn is where we pick, right? Something like that. So in this case, if you see a sharp turn over there where the rest is just steep, that's where you choose, right? So in this case, we can say that the number of clusters we want is 4, right? And I mean, for if there's like a model that you want to deploy, right? You can consider say 3, 4, and then 5, and then see which one is actually giving you the best cluster. All right. So instead of maybe just considering just 4 based on the plots that you're seeing, you can consider say 3, 4, and then 5, and then see which one is working better for you. All right. And if you choose very small cluster like this, right? If you choose very small cluster, it means that you are just having only one big cluster with no difference there, which does not actually make sense, right? It means that you're putting all the pregnant women and then those who, I mean, the young guys who also buy phone and laptops and stuff, like you're putting all of them together as one. And then you're having no difference in the clusters. You are not actually going to be able to study their behavior and target them with the right products. All right. So if you choose huge cluster or just one cluster which is having all of them together, then that is another problem too. Okay. So we use what is called the elbow method to do that. So we get the ideal cluster. Okay. So let's go to the code. I mean, enough of this one. Let's go to the code and then see what we can do here. So before that, is there any question that anyone wants to ask, or can we
Yes.
move on?
What are the limitations of K-means clustering? Is there any
Okay.
limitations with K-means?
Each of the algorithms are having their own limitations. I mean, it's like, for instance, you are using we have K that you have to choose, right? You need to choose the ideal K, right? So you choosing the ideal K is subject to your own intuition. So the particular data scientist who is building the algorithm might decide that, okay, if I choose, say, 4, right? Maybe according to my eyes, I think 4 here is actually going to do better, right? But if a different data scientist is going to build this algorithm, maybe the person thinks that we should go further to say, to say the number that is here, maybe 6, right? To say 6, right? Now we have 2 different people who are building the same algorithm using their own judgment, right? We are using our own personal judgment here. For me, I thought 4 is better. The other data scientist thought 6 is better. So now, which one do we pick? All right. So this is one big disadvantage of K-means clustering. Choosing the K, right? Is actually a big problem here. All right. So although the
Will it
elbow method actually helps, but it sometimes has a flaw. That's why in production you don't just base on K-means, or you don't just base on KNN, or you don't just base on naive Bayes, right? You build several algorithms, you tune the hyperparameters to see which one is doing best for you before you compare these accuracies for each of these, and then you choose the best one for you.
affect a number of variables I use?
Number of variables, as in what?
Yes, number of variables which I'm using, will it affect the K-means clustering?
I don't actually get the number of you mean the number of data points? Let's say in this case.
Number of features you can call. Number of features.
Yeah. Depends on the number of features. It would depend. Like here I'm using yeah. Okay, with this simple example, right? I'm saying 4, but your data set can come like 10,000, right? Like 10,000 data points in there, right? Maybe 10,000 rows. Then you have about 11 columns, right? In there. Okay, this will be a huge data set, right? This will be a huge data set. It means that the number of classes that you're going to have is not going to be the same as this simple one that we are building over here, right? It's going to change altogether, right? So depending on the number, the particular data set that you're working on, right? It's some of the data set can be huge, but you still need simple or few clusters to give, right? Some of them might be small, but you still need huge clusters, right? For example, if you are in health, you are building this for health sector, for instance, right? Some of the diseases are having different clusters. Consequences and characteristics. All right, so you need to cluster those patients into different clusters so that the doctors can actually know each patient and each disease, right? You can have that, okay, this kind of symptom is common in this group of people, right? So the doctor can actually deal with this group of people based on the symptom, right? So cluster those people into one group, right? Some of them are having, say, cough, right? And then they also visit the washroom quite frequently. They have fever. So that's characteristics of those kind of people. You put them in one cluster. Another cluster will be these people have headache, right? They have headache, they feel tired, something like that. They face difficulty in sleeping. You put them in one different cluster. All right, so it's going to be different features and different clusters that you're going to build and then cluster them into that, right? And then you give that recommendation that, okay, these are the clusters that I have. So from there, the doctor take it from there, right? They will know how to actually deal with those different clusters of patients. All right. I hope it's clear.
Yes.
All right. Is there any more questions, or should we move to the code? Okay, so over here we are going to use technical support data, right? We're going to use a technical support data. Normally, for instance, if you buy a phone, for instance, you'll be calling. Let's say they give you a warranty, right? You'll be calling them. If you see any faults, you'll be calling the customer care that I have this problem, I have this problem. And even if you call, they will ask you whether it's a sales problem or it's a technical problem that they should direct your call to the technical support team, something like that. So these are data that came in, right, from different complaints, right, from different complaints. So we're going to work on that, right? We're going to work on this technical support team data, technical support data, right? So this is different complaints that people were lodging, right? And then they put everything together, and that's what we are going to work on for this KMeans problem. All right. So these are just the normal libraries that you always be working with. All right. So we have our pandas here, the NumPy, the Matplotlib inline, Seaborn is here, train test splits. I think all of these you are familiar with them, right? What we are going to work on today is this KMeans. All right, so from sklearn.cluster, right, we are going to import this KMeans. All right, that's what you're going to use. Okay, I hope all of these libraries are familiar to you. All right. Okay, so from there, what we are going to do is actually read this data set, right? You can find this in the UCI, right? If you go to the UCI machine learning repository, is there, right? and I'll put it on the platform for you so that you can easily download and then load it if you want to practice on that. Okay, so we're going to read this CSV file, right? We're going to read it, and then after that we save it in a variable called text support df, right? We save it in that. So we can also see the shape. Now we have, with this one, we have only 23 rows with 8 columns, right? We have only 23 rows with 8 columns here, all right? Okay, we can also see the head of it, and then in the first 5 rows, and then see what we are going to deal with over here. So let me zoom out a bit. Okay, so instead of the first 5 rows, let me just try and then run this. Okay, now you can see here, right? If you see the problem type, right? We have problem type here. Okay, we have problem type here. And this problem type, it consists of several problems, right? Temperature control not working, power cord does not tightly fit, fan swing not working, main switch does not work. I mean, a lot of complaints that people were giving, right? And then they put everything together, right? Remote keys get stuck, unable to operate menu from remote, no motor noise from the system, pressure holder stuck, factory settings not working. So a lot of complaints that people were complaining, they put all of them together as a data set, right? So some of them are, I mean, relating to, we have number of cases, we have the average pending calls, right? The number of calls that they gave, and then the average resolution time, right? The number of time that the technical support team took to resolve this issue for them, right? Average resolution time is here. Recurrence frequency, how frequent these complaints were coming, all right? And then the warranty percentage, post warranty, and then we have group here. I have to actually run this because this is not supposed to come. So let me just run this again. I have to actually run this first. Okay, so up to all the way up to post warranty percent, right? So these are the complaints, different complaints and different features that we have over here. So it's a small data set that we're going to work on, all right? So let me just limit it to the first 5 rows so that you can just see the head of it. You can have space. Okay, so I'm going to do this. I'm actually going to run everything at once. I'm going to run all cells. Okay, so I'm just giving 1 second. It's actually running, right? I want to run everything so that I'll not be running it over and over again. Okay, almost done. Yeah, now done. Okay, so now this is just the first 5 rows, and then over here, as you can see over here, right? What we are going to do is to select from the first column, right? From the first column to the last one, and then we select all the rows, right? And then we store it in what is called the text support attribute, right? So what we are doing is that we are leaving the problem type because we don't actually need the problem type to actually build the algorithm. We only need this part from the number of cases all the way to the post warranty percent, right? We don't need these complaints, right? These are complaints that is actually helping us to know the type of complaints that came, right? And what we are going to actually use to build this algorithm is the features that we have here, the number of cases and the average pending calls, all the way to the post warranty percent. So what we're going to do over here is to select everything, right? Select all the rows, right? All the we have 23 rows, so all the 23 rows, and then we select from the one. Remember that this is 0, 1, 2, 3, all the way to the last one, right? So we are not selecting the 0 position. We are selecting from the 1. That's why you see 1 and then everything after that. Okay, we're selecting from 1 and then everything after that. All right. Then after that, we want to scale it because if you see the values that we have in here, right? We have some 170, we have some 12, 3. I mean, 0.04 is 0.0, 0.7 is kind of inconsistency here, right? 125, right? Some huge values and some small values, right? So we want to have a common mean and then a common standard deviation for each of these columns, right? Each of these columns with a mean of 0 and then a standard deviation of 1 for each of these columns. So we're going to use the z-score. We're going to apply the z-score on that, right? On this text support attribute that we got. We're going to apply this z-score on that. Okay. So maybe I can print this one for you to see. Okay, now if you see this one that we have here, the text support scaled, right? The scale one that we have here, you can see that each of them is it's now very small values instead of having 170, 3, 12, and then some 75, some 0.0. You can see that they are all inconsistency now. They are more consistent now. All right, so that's what we wanted to actually do. Okay, let me get rid of that. And then this one is a pair plot where we are plotting the pair plot so that we can actually see the correlation that is existing among these attributes. All right, so what we are doing over here is to use the Seaborn, right, SNN dot pair plot, and then our text support scaled, right? That's what we did over here. We scaled our data and then we store it in text support scaled. All right, so that's what we are going to use over here. And then the diagonals, we want it to be KDE, which is the kernel density, so that we have this smooth distribution here, right? So that we have this smooth distribution here. I mean, by default, it's going to give you histogram, right? And we want to see how it is being distributed with respect to the normal distribution, right? So if you can see what we have here, you can see that it's almost normally distributed. And I mean, we have some peaks in here, which is giving you some clue as to how many clusters that you're supposed to expect. Right? Some of the features are having some 2 clusters that you can actually see, some 2 peaks in there. You can see this one is actually pointing to something different. 1, 2, 3, 4. Right? It's actually showing us something different here. Right? It's actually giving us a different clue. But maybe 4 clusters might work for us. Right? This one is showing us maybe 2 might work. And we're not actually going to base on that. We're actually going to test. We're actually going to do that airball method and then see how well it's going to help us to choose the number of classes. If you see the distribution that we have here, the scatter plot is just not having any direction. So there's no correlation among these, right? So we will not be facing the difficulty of multicollinearity here. All right, so we're going to use this airball method, right? So instead of just choosing the number of classes randomly, we are going to use the airball method here. All right. So let me just take you through this elbow method.
It's 10 o'clock.
All right, let me just take you through, and then when I run it, you can actually get to understand what you're doing over here. We are going to use what is called the seed-based, right? The seed-based is nothing but it just calculates the distance, right? The pairwise distance, right? If you can see over here, the pairwise distance of the input that you give, right? So based on the distance of 2 points, it will calculate the distance of 2 points, right? And then it will actually find the minimum of that. Remember that we want to minimize the variance that is existing among the centroid and then each of the points, right? As well as each of the points and each other, right? We want to minimize that kind of I mean, the variance, we want to minimize it, right? So that's what the seed-based is actually going to help us to do that. It's actually going to compute the distance between each pair of the points, right? And then give it to us. So instead of just choosing any number of classes, say 4 or 5 or say 7, all right, we're going to test number of clusters ranging from 1 to 10, right? We are going to test number of clusters ranging from 1 to 10. So we are going to test the clusters being equal to 1, the clusters being equal to 2, the clusters being equal to 3, right? So this is just equivalent to having the K, right? the k being equal to 1, or the k being equal to 2, or 3, or 4, all the way to 10, right? So we test different case and then see. So this is actually going to be replaced here. So it is going to remember we are using for loop here. We're going to use for loop here. So it will check for k equals 1. It will check for k equals 2. It will check for k equals 3. It will check for k equals 4. It will check for k equals 5, all the way to k equals 10. Right? That's what it's actually going to do for us over here. Okay. That's what we are going to actually test. So we're going to test for different case, and we're going to use for loop for that. We're creating an empty list here, right? Where later on the different k values that, or the different results that we get for our algorithm using the different case, we are going to put all those in this empty list, right? So if you can see append here, we are appending everything in that empty list, right? So we append everything in that empty list. Okay, so when we put n clusters, so as if you remember when we are dealing with this, I mentioned something called n clusters, right? Number of clusters that you are going to use, right? And then the maximum iteration, right? That's what is happening over here, right? That's what's happening over here. So we're going to choose the number of n clusters. In this case, we are saying we are not choosing just any, say 4 or 5 or any of them. We are going to test from 1 to 10. That's what is happening here. And then we are using our k-means to do that, right? And then we initialize it and then store it in a variable called model, right? After that, we use model to fit, right? To fit the text subscale. Remember that we have that data up here. If we go up, right, we scaled our data here, right? We scaled our data here, and then we store it in what is called a in the text subscale. All right, so that's what we are actually going to do. Remember that in this case, we are not having a target, right? Unlike the previous data set that we were working on, where we try to predict whether something will happen or not, right? Something like that. Maybe we'll be having the data sets, right? And then some particular column, right, will be, say, y. We will indicate that as y, maybe some 0 or 1 or something like that. We try to predict 0 or 1. In this case, it's not like that. In this case, what we are trying to do is to use features that we have here to, group them into similar characteristics, right? To group the complaints, the various complaints, or the various complaints that will come later on. We'll be able to group them into similar characteristics so that we forward it to the right department for them to work on, right? So any complaint that will come, maybe someone calls that, oh, my battery is not working. Then we know that this is actually this complaint is actually supposed to go to department B. All right. Sorry. All right. So if a different call comes in that, oh, my phone charger is no more connecting, then we know that, okay, this complaint is supposed to go to department, say department A. All right. So based on the clusters that we create, the company can actually create different complaint departments for each of these complaints. All right. Or maybe different team, maybe team A, team B, team C. Each of the team will be working on different problem statements. All right. So maybe one team will be working on the battery of the phone. One team will be working on the charger of the phone or something like that. All right. So as soon as a call comes in, we will be able to direct that call to the particular department. Remember that these days there's something called the automation. All right. So the call centers are no more people sitting there making the calls. So as soon as someone calls in, the bot that is being created, right, it's just a bot, right? So as soon as someone calls in, the bot will direct the call to the particular team that is supposed to pick the call, right? So as soon as you call, the bot will ask you, can you specify your problem? If you specify your problem, like my battery is not working, the bot knows that it's team A, which is working on battery. Then it will automatically redirect your call to team A. All right, so that's what is actually this clustering is actually being used on the industry. All right. So over here, as I said that after everything, we append everything in this list that we have here. All right, and this one is nothing but finding the minimum. Remember that we are trying to minimize everything. So cdist over here, right? The cdist will actually help us to calculate the distance which is existing among this text subscale and then the model clusters, right? So the centroid and then each of the points, right? So this step here, right? This one that we have here is containing some points, all right? This one is containing some points. And then this clusters, right? This is the clusters that we want. So maybe these clusters could be say 5 clusters or something like that, right? So each of these points are going to be associated with the different points that we have, right? So let me use this, right? So maybe we have 5 clusters, right? So 3, 4, 5. So these clusters might represent different teams, right? Maybe team A, which is working on the battery. Maybe team B, which is working on say the phone charger, right? Team C, which is working on say the screen or the phone, right? The phone screen. And then maybe team C, team D, right? They are all working on different problems. So as soon as the call comes in, the bot will actually pick the call and then redirect the call to the respective team so that they can work on the problem. All right. So that's what cdist is actually going to do: calculate each of the points and then the centroid. All right. And in this case, we specify that it should use Euclidean distance. All right. Then we divide it by the total. I divide it by the total, and we are using dot shape equals 0 because we want to plot it over here. If I scroll down a bit, all right, we want to plot this one over here. So we make it just a single I mean, just on a single line, so that we can actually plot it over here. All right. Otherwise, we'll be having something like this. Let me close this. All right. Otherwise, if you can see here, we have this one here, and then we have this one here. Right. So just a single array. Otherwise, we'll be having one here, something here, something here, which is going to be difficult. Or maybe even if it's 2 of them, something like this, something like that, which is going to be difficult. So we want all of them to just have just this single. Let me undo. Yeah, only this and then that, right? Which will help us to actually plot them here. The mean distance, right? Which will help us to plot them over here. Okay, that's what this part is actually doing. That's what this part is actually doing. Okay, so after that, we append everything in this mean distortions, right? So if we see what is in the mean distortion, we have this, right? All these are just the sum of the minimum, right? Remember that we say that we are minimizing everything, right? So we find each of the points, right, minus the mean, all right, minus the mean divided by the total number there, all right? And then we sum everything, right? That's what is happening here. We sum everything. We find the minimum of that. All right, that's what's actually happening over here. Okay, so over here is, it's just plotting everything that we have here, the mean distortion, right? We are plotting everything that we have here. Now, if you see the graph that we have, the code is just simple. This code is just simple. We have the plot. We have our plot function here. We have the clusters that we want, right? Remember the clusters, we say that we want clusters from 1 to 10, right? That's what we have here. Then we have our mean distortions. This bx dash is just to plot this, to have this dash that you're seeing here, right? Then it will give you some x ticks that you can see over here. That's what this part is actually going to do, all right? And then you can see we have some k here, all right? We have some k over here, right? The k is just here. That's the x label, right? And then the y label is mean distortion, as you can see over here, right? And then the title is selecting a k with the elbow method. That's what you see here, right? So that's just the code. So let's see what is behind this one. All right. Now you can see that the mean distortion, right? The mean distortion. So as the cluster, right? The cluster. Remember that's the k that we are selecting, right? So if the k is equals 1, then we have high mean distortion here, or the high variance here. Okay, so as it keeps on increasing, right, as it keeps on increasing, you can see that it keeps on decreasing as well, right? This actually keeps on decreasing, right? And then over here you can see that there's a 10 here, all right? There's a 10 here, and then it keeps on being a bit steep, and then from here again there's another 10, right? And then from here it becomes a bit slow. All right. So in this case, maybe one, if I am building this, maybe I can say that, okay, this is where the sharp 10 happened, right? So I'm actually going to choose this, right? I'm going to choose 3. So I'm going to say that, okay, then I'm going to use, let me get rid of, I'm going to use k equals 3, all right? Someone might say, okay, no, this one happened here, right? So I'm going to choose 4. Right? I'm going to choose say k equals 4, right? And then maybe another person with their own intuition might say, no, I will consider 5. So another data scientist might also consider say k equals 5. Okay, so that's as you were asking if there are any for or there are any disadvantage. So this is some of the disadvantages, right? Different data scientists might choose different Ks, right? Which will give different clusters, of course. All right. So in this case, you can consider 3, you can consider 4, you can consider 5, right? You can consider either of these, and then after that, if you see, if you run if you build algorithm on this, and then you see the complaints that are being associated with these clusters, and then it makes sense to you, right? Maybe you choose 4, and then you choose 4 clusters, right? And then you see the number of complaints that are being associated with each of these clusters, right? If it makes sense to you, then you can go with 4, right? And if it's actually overlapping, some of the complaints are overlapping. Maybe someone said that my battery is not working, right? And then someone said that my charger is not working. Now it gives battery is not working into different cluster. It gives charger is not working in different cluster. But according to you, charger is not working and battery is not working should be for the same team to work on. All right. Then you can see that, okay, then I have to reduce my clusters. All right, because I'm giving too many clusters, it's actually giving the complaints to different teams instead of similar complaints going into going to same team, right? It's actually giving those complaints to different teams. So now I want to reduce it from 5 to 4. So you might end up seeing that, okay, battery is not working. It's actually battery is not working, and charger is not working. It's actually being put into one cluster, right? And one team can work on this problem because they are similar problem that one team can work on. All right. Is there any question here? Okay, so we're going to actually consider k equals 3, right? So now we use k over here from k equals 1 all the way to 10, right? So with this elbow method, we can say that we are going to consider k equals 3, right? Let's consider that, and then we can also maybe consider k equals 5, right? We can also consider that. So at first, let's consider k equals 3 and then see. All right, let's consider k equals 3. So now you can see the final model, or this one is just a variable name that I'm giving over here. You can choose a name. Right, so k means, and then the k is actually going to be 3. Don't forget the other hyperparameters that you can add to this, right? In this tutorial, we're not interested in the various hyperparameters. What we are interested in is the number of k and the number of clusters that we are going to get. All right, that's why you just see 3 here, right? But if you don't specify any other hyperparameter, it's going to use the default for all of them. Right? If you want to see all of them, you can just see the KMeans documentation, and then you can see all the hyperparameters that you can use. All right. So after initializing it here, we are going to use it to fit this, right? To fit on the text subscaled. That's our data that we have, right? Then we use it to make some predictions, right? We use it to make some predictions over here. All right. Use it to make some predictions over here. So now we're going to create another column, right? Remember this is our original data here, text sub df, right? if I should go all the way up, all right, text sub df is here. All right, this is actually our original data. So we are going to create another column. Remember, we have it to be from problem type all the way to post warranty percent, right? So we're going to create another column here, right? We're going to add another column here, which is called cluster, right? So that we see that, okay, with this problem, which is having these attributes, right? Let's say temperature control not working. We had this 170 number of cases. We have average pending cost 1.3, average resolution time 32, recurrence frequency 0.04, replacement percent 0.0, warranty, right? In warranty percent 75, post warranty percent 25. So we see the number of clusters that they to put this complaint according to this attribute, right? According to this attribute. So we see that for all of the data points that we have here. That's what we're going to do. So we're going to add another column here. All right. That's what we are creating now. So let me go all the way down. That's what we are creating over here. So we're creating another column, right? We're creating another column here. Then we add our predictions. Remember, we did a prediction here, right? Then we add that prediction over here. Then we see the first 5 rows for that. So let me get rid of that so that we can see over here. Now you can see that now clusters have been attached to this, right? You can see over here that we have clusters here, right? And then since we specified that the number of K should be 3, that's the number of clusters should be 3. We have we will be having 0, 1, 2, and then 3, right? I mean 0, 1, and 2 actually. Undo. Okay, let me get rid of this one. All right. So we'll be having 0, 1, and then 2, right? That's three different clusters, right? So some clusters will be put in 0, some clusters will be put in 1, some clusters will be put in 2, right? So we have 3 different clusters that is going to happen here, and we can also see which complaints or which attributes are being classified as classified into cluster 1. Cluster 0, and then cluster 1 and cluster 2. So let's see that one and see. Okay, so over here, if we do this, I'm going to actually comment this one out. Okay, now if we do this, right, text sub df, and then in text sub df we select the cluster, and then we say that where the cluster is equal to 0, right? So that's what is happening here, where the cluster equals 0. So that's selecting the clusters that have been associated with 0, right? So we can see that all these are in cluster 0. All these complaints, we can just see only the complaints, right? You can specify only the problem type, so that we see only which kind of problem types. All right. So now if you can see here, you can see that we have power cord does not tightly fit, main switch does not on, cluttered with pop-up messages, motor noise from the system, battery backup does not get fully charged, battery does not last full 8 hours, fan speed. So you can see that this is actually power problem. All the power problems have been put into one cluster. All right. All the power problems have been put into one cluster. Maybe cluttered with pop-up messages, something like that. Maybe this one was wrongly classified. So maybe you might think twice, something like that. All right. But you can see that mainly the problem that is relating to the power problem have been clustered into one, right? We can also see those that are in cluster 1, right? Let's see the kind of problems that are in cluster 1. So now if we change this one to 1, you can see that forgot mobile app password, AC stops apparently, app hangs while entering commands, reinstalling the app hangs the phone, mobile screen blanks on use of phone, AC remote does not work, factory settings. So you can see this one is more like operating of the phone problem, something like that, right? The password, the screen of the phone, something like that, right? All those problems that are similar to each other have been put into one cluster, right? In cluster 1. We can also see those that are in cluster 2. All right. In cluster 2, you can see temperature control not working, fan swing not working, app takes a long time to initialize, unable to connect the app to the device, AC controllers, software missing, remote keys get stuck, unable to operate menu from remote, freshener holder stuck, Wi-Fi connectivity break. So I mean, similar problems also put into in a different cluster, right? More of the temperature, the control, something like that, right? All of them in one cluster. So all these are common problems that one team can work on, right? So you can give, I mean, you can associate these kind of problems. So in the future, if someone calls and then the person complain about, say, their temperature control not working or fan swing not working, you can say that, okay, the bot will direct this call to, say, the team 2, right? Then the team 2 will pick up the call and then try to help that customer. All right. So basically, that's what happens in the industry, right? With the KMeans algorithm, it's basically what they use for in the industry. All right. We can also consider k equals 5, right? Since this, we can see 1 sharp turn here. We can see some here, which after that the rest are a bit steep, right? So we can also consider maybe k equals 5. All right, so if we do that, it's just the same process that we followed when we chose k equals 3, right? So we are going to do the same thing, with the exception of the fact that we're going to use k equals 5, right? So if we use k equals 5, we can have this, we can initialize it, right? And then after that, we fit it on our data, and then we make some predictions, just the same thing that we're doing. And then we create another cluster again, all right? Then we put our predictions there, all right? So now if we see the head of that, let me print this one. If we see the head of that, so now instead of having 0, 0, 1, and 2, right? Instead of having 0, 1, and 2, now we'll be having 0, 1, 2, 3, and then 4, right? So 5 clusters. All right, we're having 5 clusters. That's 1, 2, 3, 4, 5 clusters. Okay, so we can see which components are in each of these, right? In each of these clusters. All right, I'm going to actually get rid of this. I'm going to comment this. Okay, now we can see. Let me run this one here. And then instead of getting all the attributes, I'm just going to see only the complaints here, right? I'm only going to see the complaints. Okay. Now for the complaints that are in cluster 2, when this is when we choose k equals 5, right? Remember what we were doing earlier on, k was equal to 3, so we're having 3 clusters. Now we have 5 clusters. All right. So when k equals 0 k equals 5, right? We see that, okay, in cluster 0 we have power cord that's not tightly fit, right? Main switch does not on, cluttered with pop-up messages, motor noise from the system, battery backup, right? So this one is almost similar to what we're having when we use k equals 3, right? It's almost the same, right? If we, but because I've run it again, it's actually has overwritten this one, right? So this one will not actually make sense again, right? This is the cluster 5 is the one that is going to work. So we can see those that are in 1, right? Forgot mobile app password, AC stops abruptly, reinstalling the app hangs the phone, mobile screen blanks on use of AC, use of phone, AC remote does not work, factory setting not working, right? So similar problems being clustered into being clustered into similar clusters. All right, let me go to the last one, all right, and let's see. Let me run this thing again here. Okay, now you can see in cluster 4, right? We have power cord does not tightly fit, main switch does not on. Now you can see this, you can see a problem here that we have only these two problems being given a whole cluster, which does not actually make sense. All right, so we will not consider cluster 5. I mean, k equals 5, right? It does not actually make sense, right? Because this problem is a problem that is happening in a different cluster, and then it has also been given associated here, right? Which does not make any sense. We cannot give a whole team to work just on power cord that's not actually fit and main switch that's not on, right? We this problem can be done by other cluster, maybe by cluster 0, right? By cluster 0 can work on that. I forgot mobile password and something like that. The guys who are working on this problem can work on the same problem that are happening in cluster 4, right? So we will not need this many clusters, right? For this particular problem, we will not consider the whole of this, right? For k equals 5, right? We will not consider that. Okay. So in this case, we will say that, okay, for k equals 3 makes sense. So we're going to use k equals 3. And this becomes our final algorithm that we will use for our industry or for our company. All right. So that's k-means for you. If you have any question, you can ask.
What are the other hyperparameters we can fine tune?
If you want to see all the hyperparameters that I said, you can also check. You can always check from the just copy this, right, and then go to the documentation. You can see a lot of them over there that you can use, and the various explanations to them. Right. So if you go to the documentation over there, right, you can see that we have a lot of the n clusters, right? We have the inits, k-means plus plus. That's going to be the default, right? And init max iteration to remember we did not specify the maximum iteration that we are going to use, right? As I said, the iteration is actually being done so that I'm using this Elliott theorem, right? So that this is actually being moved and different points are going to be associated with different um, centroids, right? We did not actually specify, so by default it's going to use 300. All right, so there are a lot of them, and then you can see each of these hyperparameters and their explanation here. You can see sample examples that they are using over here, right? So we can come back and then change each of these, right? You can just start by adding your own. I mean, maybe max iter, right? Maybe max iter should be, so instead of 300, maybe you want to do that for 500 times, right? So you can come back and then change everything and then run it and see what you are getting, right? Or if you're doing, you are building an algorithm for production purpose, you're going to do this, you're going to be running this um, different times to see which one is actually working best for you, because you cannot actually risk it for the company to lose money. So you actually run this to see which iteration is actually going to be better for you. If you choose, like for instance, max iteration, for instance, if you choose say 10,000, right? It's actually going to make no sense with respect to the data that we are using. It's quite small. So it will get to the point that it will keep on running, but it's not going to associate the point to any thread again. It's not going to work again. It's just going to give you the same iteration over and over again, right? It's not actually going to do anything. So you can actually change each of these, right? So just play around it. If you want to see, you can get everything from the documentation. All right.
Can we check the confusion matrix of this?
What?
Confusion matrix.
Of course, you can build a confusion matrix for that. We did not do that because we've done that in previous in our previous what do you call it? In our previous class, we've been doing confusion matrix for all of them, right? So even this one, I did not use the train test split. If you recall, we did not use this train test split, right? So all these are just something that you can use by yourself. You can choose to do or not. You can just do that. Remember that in this case, we don't have any targets that we want to predict, right? We don't have any targets here. We just want clusters, right? What we want to do here is clusters, right? We want to create clusters so that we assign, say, team A, work on this problem, work on problem 1, right? Say team B, right? Team B work on say problem 2, right? Say team C. That's what we want our company to do. Work on problem, maybe problem 3, right? You want to create clusters which is consisting of different problems. All right, that's what we want to do. In this case, we don't have a target. So some of the things that we've been doing, we will not actually need it in this case.
How do we cross-validate whether our K-means clustering giving proper result for our data set?
How do we do what? I did not actually get your question.
Cross-validate.
How do we cross-validate? Okay, you can use a score, right? You can use the score. Remember that, as I said, we did not use that because we've been using it in our previous classes, right? So you can use that. It's actually in matrix, right? In matrix, there's what is called a score. So you can use score, right? And using the confusion matrix, you can even use that one to actually get to know how well it is doing, right?
Okay.
So you can just refer to the previous videos, the previous notebooks, and then you can see it's just the same way because we've done some predictions here, right? We did some predictions, we did some predictions. So all you need is just this prediction variable here to check the score. So you can
How
just
do you know that
and then you
grouping is correct?
what?
How do you understand that the grouping is correct? Like it is not putting different problem types into the same
Okay,
group.
that's what I did over here. So now if you choose say k equals 3, let me go up, right? If you choose k equals 3, right? If we choose k equal, yeah, over here. If we choose k equals 3, right? We have 3 clusters, right?
Yes.
We have 3 clusters, which is 0, we have 1, and then 2. Okay, so 0 is going to have different problems, right? 1 is going to have different problems. I mean, in this case, complaints, right? Right, and 2 is also going to be associated with different problems. Okay, now you yourself know that these are the questions that are coming, right? Now you've divided your team, the team that is working for the company, into say team A, team B, right? Team B, team C, all right? And these ones are having different set of skills, right? There are those who know how to work on the battery. There are those who know how to work on the phone screen. There are those who know how to work on the say on the power cord, right? On the power cord. Now, what you want to do is that if a complaint comes, which team should work on that complaint? Sorry, which team should work on that complaint? All right, that's what you want to do. So now, if a call comes in, right, if you build this algorithm, it's going to use the previous calls and the previous complaints that you have, right? So this cluster is having set of problems or set of complaints. This cluster 1 is having set of complaints. This cluster 2 is having set of complaints. Okay. Now, if a new call comes in, right, then maybe this cluster is having complaints which are relating to the battery of the phone. Okay, this cluster is having complaints which are relating to say the power cord, right? The power cord of the phone. This cluster is having something which is relating to say the screen of the phone, right? Now, if a new call comes and then the customer say my battery is not working, quickly this algorithm will direct this this call into this problem, right? Into this cluster rather, and then whatever algorithm that you built and the bot that you have, right, will direct the call to say team A. Team A is the one that works on battery. So now team A will take over from here, right? And then now talk to the customer. However, if this customer was to say my screen crashed, but you gave me warranty for 1 year, so I can now come and then repair it, right? Now, this will be going to this cluster, which is cluster 2, right? And then it will say, okay, team C is the one that works on screen. So this call will be redirected to team C. And then team C will now talk to this customer and resolve it. All right. However, if you build the algorithm, if you say that, okay, I'm using K equals say 5, right? Now K equals 5 is going to add 3, 4, right? Now you have 5 clusters. However, this last one is having only 2 problems which is being associated. Maybe the fan of the phone, right? Maybe something like that, or the phone heats too much, right? So maybe the ones that work on this one, right, is the same team, is team A that works on that. But instead of your algorithm putting this complaint in cluster 0, so that when any calls come, cluster 0 will direct that call to team A, right? You've now created another cluster here, which is now becoming too much. And now if a call comes, it becomes difficult and confusion here, where you should direct it, whether you should direct it to team C or direct it to team B or direct it to team A, right? Now you print out, right? Remember that when we did this, we printed everything out for K equals, let me do that again. For K equals 5, right? For K equals 5. Now, if we use the last one, you can see that only 2 problems are there, which does not make sense to create a cluster, a whole cluster, or a whole team, right? And pay people to just sit and then work on only the power code, right? So according to your own intuition, as a data scientist or as the stakeholder who is maybe your supervisor or something like that, right? Now he will say that, okay, this one is not necessary. We cannot create a whole team for this. So now we should limit our algorithm to only, or our team to only, or our cluster, right, to only 3, right? So in this case, we are going to have only K equals 3, right? So together,
Sorry,
Hmm.
sorry, I have a question here. I probably am not clearly following. Maybe it's a silly question here. Still,
Oh, it's fine. You can just.
yeah, you have removed the problem type actually when you are doing using the data set. So how does that, when a new call comes, how's that, does it know is it is a problem related to a battery, or how is that grouping being happening, because you have already removed the problem type and you have kept the rest of the columns.
Okay.
So
Now, what's actually happening over here, right? What's actually happening over here is that we are not using the problem type. We are not using the problem type, right, from initial parts. Yeah, we remove this. Where did we remove? Yeah, over here, right? We remove the problem type from here. Now, what we are saying is that we are not going to use the problem type to actually build the algorithm. We already have these features, right? Number of cases, average pending calls, average resolution time, recurrence frequency, replace percent, in-warranty percent, post-warranty percent, right? We have these features. So based on these features, we want our algorithm to learn on these features. After learning on these features, right? After learning on these features, it will associate these features into clusters, which of course, these features come with these problem types. You understand now? These features are associated with this problem type. We are not building the algorithm, of course, on this problem type, which we are building the algorithm based on the features that we have here. And these features are generated based on the problem type. So algorithm will learn from these features, which of course is associated with this problem type. So if we add our cluster here, all right, if I go down, let me go and then change this one so that you can actually get it. Over here, I wanted to print only the problem type, right? So now if I take that one off and then I print everything, right? Those that are in cluster 2, you can see that the clusters is here, right? And then you can see that we have the cluster here, okay? And then we have the features, right? Which of course are associated with this problem type. Okay, so now the problem type AC stopped abruptly is put according to the features that we have here, is associated with cluster 0. I mean cluster 2. All right.
okay, yeah,
AC root does not work is associated with cluster 0. It's based on these features that we have, right? Based on these features that our model learns from. And of course, all these features are associated with this problem type. So if these features are associated, these features get being clustered into these classes, then of course it comes with these problems automatically.
Okay.
Okay.
Also, we have used, we have scaled down the values of all the variables.
Yes.
Is it necessary to have always to scale down the values? Can't we use directly actual values?
We can actually you can decide not to scale it, but the problem is that if you don't scale it, right? I mean, scaling it is the best practice to actually do. Is the best practice to actually do. It's actually going to ignore some of the features that you have. All right, it's actually going to ignore if you see the original data that we are working on. All right, the original data is having like for instance you have 170 here, right? We have say 3 here. We have let me consider this. We have 0.0. We have say 0.7, right? Now remember that Euclidean distance, right? Euclidean distance is actually going to use say x1 minus say x2, all right, squared plus say y1 minus y2 square plus whatever up to the last one. So it's going to actually find let me get this. So going to find the distance between 170 and 12. It's going to find the distance between 170 and 5. It's going to find the distance between 170 and 3, 170 and 45, all the way to the last, I mean 170 to the last one, the last data that we have. All right, it's going to do the same thing for each of the columns. All right. Now, what is going to actually happen is that if we don't scale the data, now if we find the distance between 170 and say 12, or 170, let's consider 170 and 3, right? So let's do something like that. 170. Remember this is root, right? 170 minus say 3. We find the square of that plus now 170, right? Let's trace that one. So that would be say 0.0 minus 0.7 squared. Now what is going to happen is that 170 minus 3 is going to be a huge value. If you find the square of that, is going to be very huge value. However, 0.0 minus 0.7 is going to be a very small value, even if you find this, the square of that. So what is going to happen is that whatever information is here is going to be ignored, right? The algorithm is going to, I mean, ignore this information that is very small, it's very, I mean, minute. It doesn't count. Meanwhile, there's information here that we want to know is I mean, replace percent, right? How often they replace, I mean, those like temperature control not working, how often we're able to replace that problem with a different part for the, or a different accessory for that customer. We want to know that information, but Euclidean distance will ignore that information if you don't scale it. However, if you scale it, they're all going to have a consistent number, which is mostly 0, mean equals 0, right? With a standard deviation, right? SD of 1, right? So it's going to be, all the values are going to be between 0 and 1, which means that no value or no distance between each pair of the points is going to outweigh the other. All right, so we are not going to lose information. But if you don't do that, it's going to ignore some of the information that you might end up losing, right? But you don't want to do that. You don't. This is a crucial information you want, but your algorithm will not understand that it's an important information.
So can we do like this? Before using the scaling down, can I go with the outlier detection and then I can scale down? Will it affect my results?
Can you come at
What if I use outlier detection? So then I scale down the values. Will it change my results?
Okay, it depends. It depends on the outliers that you remove and the kind of treasure. I mean, the kind of um, there's a technical word I'm trying to recall. I mean, the kind of threshold, the kind of threshold that you set, right? Mostly we say that if the data point is greater than plus or minus 3 standard deviation, all right, then we consider that as an outlier. Right, we consider it as an outlier. Right now, if some of your data points might not be an outlier, even if you use this kind of threshold, that's plus or minus standard deviation. Right, for instance, maybe to see that, right, use the box plot, and then you see that any data that is plus or minus standard deviation. So if you see any other data which is going here, right, which is the plus 3 standard deviation, any data greater than plus 3 standard deviation, any data that will fall here will be considered as an outlier, right? And then any data that will go here minus 3 standard deviation, right, will be considered as an outlier. However, there will be some data points which ideally, according to the business problem, right, according to the business problem, should not be an outlier, but you use a threshold that any data which is plus or minus 3 standard deviation should be an outlier. If you do that, in that case, you lose a significant information, and that model that you will build will be a false model. It might predict, and you might have about 96 or whatever accuracy you have, but it will not actually reflect the problem that you're actually solving, right? And mostly plus or minus 3 standard deviation, removing outliers actually works best, right? That's why you mostly see that. But depending on the kind of problem that you're working on, you need to also use your own together with the business stakeholders, your team leader, or the particular company, right? According to what they want to actually achieve, they need to adjust this. So it could be maybe plus or minus 4 standard deviation. Then you use that to do that. In that case, some of the data points might still be captured and might not actually affect your final model that much, right? So depending on the kind of ratio that you set, okay. So mostly that's why they sometimes say that domain knowledge, right, is crucial, right? You are working as a data scientist, but you need to be in touch with the business leaders or whoever is giving you the problem to solve, right? So that you know what is important to them, and you know which data to consider as very important and which data to, give less importance to. All right.
Okay. Do we have any threshold value for ratio of the small and the bigger number when we will have to go for scale up?
Can you come again? Do we have
any threshold value or the ratio from which we can understand that we need to do a scale up or scaling?
Okay. If I understand your question, if maybe let me get this one. Let me bring my pen. Okay, you want to know if let's say we have our data points to be say 200, is we can consider this as high, so we need to scale it.
Yes, this type of things, right?
Okay. Now, what you can actually get to know that for every data set, right, as soon as you read it, as soon as you read your data set, right, using the read underscore CSV or read underscore whatever you use to read your data, right? Now, what you're going to do is to look at the individual points that you have, right? How are they varying from each other? Now, I can see 170 here. I can see 1.3. Now, this one is a red flag straight away, right? I can see 5 here. I can see 45 here. I can see 8. I can see 0.01 here. This one is actually giving me the go ahead to scale it, right? So in no way would I build an algorithm on this without scaling it, right? Because I know that it's actually going to give me a false prediction. Now you can see 1 here, right? I can see 99. So I can see that the distance between this 5 and 99, right? If I find the square of that, it's actually going to be huge, and it's going to ignore some of the distance. For example, distance between 0.7 and 0.0, right? So as soon as I see the values being different from each other, wider in variation like this, I go ahead and then scale it, right? This is just go ahead and scale it. However, you might see the data set as, I mean, maybe you might see some 1, 2, maybe 5, 4, 7, 0, 1, 6, 2, something like that, right? So then you can see that, okay, they are, I mean, a bit consistent, right? So in that case, you can move ahead without scaling it, right? But if you want to be at the safer side, you can always scale your data, which will not do anything to you, right? The only thing you have to do is that if you have a target, if you have a target that you want to predict, make sure that you take the target out. For instance, if this was supposed to be our target, make sure that you take this target out, right? Make sure that this target will not actually be part of the data that you're going to scale. Make sure that that target, you take it out, and then the rest of the data, you scale it.
Okay. Okay. Thank you.
All right.
One more thing, how do we understand which features are important in K-means clustering? So how do I check that?
The features are important.
Yeah, feature importance.
Okay. I think I've forgotten the particular problem, but I think we did something like that, right? Where we checked the feature problem. There's another one. I don't know whether it will come under hierarchical. Let me see this. There's another one that we will do like that, where we will actually get the features that are important. Okay. I think it's not this one, but I'll actually get one of them so that we can actually see. I'll get one of the problem like that, where we can, after building the algorithm, you actually fetch the features that are important, so that you see, we can see the features that are important, right? I'll do one of that problem so that we can see. I've forgotten which particular problem, but I remember I have a particular project on that. This one is also a classroom, right? You can actually visualize the various clusters that you have, right? This one, for instance, we did not actually. I think those who are in data science project training, I've seen this one. All right, this is the one that we fetch the data from the Yahoo site. Right. So in this case, we don't actually have any data. We just fetch the data like that, and then we started manipulating it. Okay, I'll get a project. Sorry, I'll get one of them so that we can actually see the features which are important. All right, I'll get one. It's better to actually see it than just me explaining it to you. I have a lot of them here, but I've actually forgotten the particular problem that is having that. I have answered, but I'll check and then I'll let you know, right? Maybe we can do that one together in class.
Okay.
I'm trying to remember the particular problem. Okay, is there any other question that anyone wants to ask?
No, I'm good.
No, we are fine.
Okay. So should I load another project? Because some of you are still having projects pending, so I'm holding on to some of the projects that because we are supposed to do. Let me see from this one. We are supposed to do one for KNN. We are supposed to do one for support vector. We are supposed to do one for clustering. I mean K-means clustering, and then one for hierarchical, right? Before the final project will come, right?
Yeah, I am in favor of giving one more. It's my personal opinion.
So I should put one more there.
Yeah, that's my opinion.
So now we have I mean, I think for logistic we have a project that's, I mean, some of you have not submitted yet, and some of you have also submitted. I mean, I've seen some of them, and so try and then complete it, right? Because I don't actually want the project to be pending. I want us to get it out of the way so that we will be good before we finish this class.
Okay, sir.
All right. So if there's no other question, we can end the class here. And then I actually planned that we will do hierarchical clustering today. We'll finish KMeans, then we do hierarchical. But I think we can do it I mean next week.
Okay.
Okay, so we will end it here.
Thank you.
Thank you.